Hello, everybody. Can everybody hear me? If you could just post it on the chat or just let me know.
Yes, sir.
Awesome. Thank you so much. All right. So let me get started with today's session. I want to do a little bit of a review of the truth tables. And while I cover the truth tables, I also want to mention about equivalent statements. And an equivalent statement is actually equivalent statements when you have exactly the same truth tables in the final column that represents the value of that statement. For example, I have show that the negation of this statement P or not Q, and the negation of it's equivalent to the negation of P and Q. And so in order to show that they are equivalent, I need to do the table for each one of them. And let me see so I actually have the table already completed, but I wanted to show you very quickly how to do this. So I'm gonna go ahead and complete this. I had it already, my tables filled out, but I'm gonna very quickly go over at least one of them. So let me do the first one just to remind you how to do it. So to create the table, make sure that you have your variables on the left-hand side. Notice that even though my tables have different symbols, the only variables that appear are P and Q. And the number of rows that your table is going to have is 2 to the power n, when n is the number of variables. So in this case, it's going to be 2 squared, which is 4. And I have my 4 rows. And the typical way of writing down the truth values, all of the possible combinations of truth and false, are usually true, 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 false, false, true, false, false. I always recommend to do this in a pattern. So I usually start with P. I do true, true, and then false, false, and then I alternate Q, true, false, true, false. Next, to complete this table, now this is the part where our previous presenter on our last Friday, it was mentioned that sometimes you will be asked to memorize all of the values, or you may be allowed to use the tables. So as I go over them, I'm just going to remind you of those values. So I would start by doing inside the parentheses. So kind of like in the order of operations, if we have parentheses, we need to start by filling out the values for the parentheses. And I'm going to go from left to right. My first variable that I see is the P. Since it is inside the parentheses, the negation does not apply to it. I'm going to apply the negation after I simplify the entire parentheses. So P by itself has the values true, true, false, and false, which is exactly the same values. All I did was copy the values on the first column, and that would be number 1. Next, I move on to the Q, and notice that it has the negation symbol. So for this one, I'm going to do the opposite values. So in Q, I had true, false, true, false. So I'm going to go ahead and do false, true, false, true. And this would be number 2. Yes, let me know if you have any questions. For now, I'm going to do the OR. So these two statements are connected by an OR. So to find the values, when you do it, it's also called the disjunction. The disjunction is true anytime that there is at least one truth, and is false if there is 2 false. So as I look at the values, I see true and false, so this is going to be true. I see true and true, so this is going to be true. False and false, this is the only time that is false, and false and true, this is going to be true. And this is my third step. Now, this column 3 is the answer for the entire parenthesis is kind of like the final answer of the statement, the compound statement that is inside the parentheses. So as I create the negation, let me see if I can change this color. As I create the negation, I am going to do the opposite values only in column number 3. So that's going to give me now false, because notice that column number 3 has a true, so the negation would be false. And then I have another true, so the negation would be false. Now I have a false, the negation would be true. And similarly, I have a true, the negation would be false. And this is my last step, which is 4. So these are the truth values for the entire statement. For not, it is not true that P or not Q. For that whole symbol, that is my last column. And in a similar way, I would create the truth table for the second expression, the one that I want to prove that it is equivalent. And let me do it very quickly. This one is actually much faster. Notice that I always start with my variables P and Q without symbols. So the 2 first columns always start the same way. I have true, true, false, false for P, true, false, true, false. And then going left to right, the first symbol that I see is not P. So I'm going to do the opposite values of P. That would be false, false, true, and true. And this is my first step on this table. Now I go on the other side for Q, and I'm going to copy exactly the same since Q doesn't have any symbols. The or I'm going to leave it as a different, the last column. This is going to be true, false, true, false. I'm simply copying the same values that I have for Q in column 2. And now I can do, now this is the conjunction, and this is only true when both of them are true at the same time. I remember the example that we mentioned was that if you're hiring someone, you need them to have a diploma, and also you need them to have the training in order to be, so you need to have both truths in order to be true. So this would be false. Since I have false and true, well, that's going to be false. False and false, that's also going to be false. True and true, this is the only time that it is true. And if I have a true and a false, the answer is going to be false. The compound statement will be false. And this was I forgot to do this, step 2, and this is step 3. So as I look at the last columns, the last one that I did on each table, they have exactly the same truth values. On the first row, they have false, false, true, and then false at the end. So I can say that these statements are equivalent. And the symbol to represent equivalent statements is, so this was, it's 3 lines. Let me just write it on the top. So kind of like an equal, but it's 3 lines, which is equivalent, 3 horizontal lines. And so this statement is equivalent to not P and Q. Okay, so that is exactly what I had on my presentation, but I wanted to do the table myself just to kind of like remind you how to do the tables, because this is something that you're going to have to do during the homework, and most likely is probably going to be in our next exam. So let's go on, and the next, the Morgan's laws are actually typical equivalent statements, and I'm going to state it for 2 variables. If you have P and Q, then this is always true. It doesn't matter what the statement are. So the negation of P or Q is equivalent to not P and not Q. And similarly, the negation of P and Q is equivalent to not P or not Q. And the way that I think about it, this is kind of like a distributive property. So this reminds us exactly of distributing, because we can think of that negation as a negative sign that you're distributing. But notice that in order to distribute it to the P and the Q, you need to change the symbol. So if you started with an or inside the parentheses, you need to change it to an and. And similarly, if you start with an and, you need to change it to an or. Now, how can we use these equivalence statements in a specific context? Well, this example is going to show us how to create an equivalent statement by using the Morgan's law. So the statement is, it is not true that I graduated or I got a job. Something to remember is that whenever you have a comma, this comma actually represents, it helps us identify group statements. So I know that since I have a comma, the two statements, I graduated and I got a job, should be in parentheses. So I'm going to start by writing all of these in symbols. So my statement P is going to be I graduated. My statement Q is going to be I got a job. And I have the or preposition, which is the disjunction. And the not true, it is not true, that's just the negation symbol. So I put the parentheses because of the comma and then the negation symbol. It is very important to have the parentheses. That's why we use we use the comma as a cue to remind us that we need a parenthesis in there. And remember that the Morgan's law says that you can distribute this. So this statement is equivalent to not P and Q. How do we write that? How do we write it down in English? Well, the opposite of I graduated would be I did not graduated. Now I'm going to change the or for an and. And after that symbol, I need to have the negation of Q. Since Q is I got a job, the opposite would be I did not get a job. So these two statements are equivalent because we know that in symbolic form, in symbols, they are equivalent. The next type of statements that I want to talk about are tautologies and self-contradictions. And a tautology is a statement that is always true. This means that whenever you do the truth table, it doesn't matter what P and Q are, you always are going to get true in that last column. Similarly, a self-contradiction is a statement that is always false. So the last column for that table is always going to have all false values. An example would be the following. It says, show that P or parentheses, not P or Q is a tautology. So I'm expecting to get all truths in the last value. Now this one, I actually created the table in here. So to answer this, in order for me to know that it's a tautology, I need to do the truth table. First of all, I notice the amount of variables. So even though the P repeats, it's only P and Q. I only have two different variables. So I'm going to have a truth table that has P and Q, my two different variables. And then I always suggest to students, whenever you do your table, kind of like space out the entire formula, the entire symbols, so that you have enough space and it's not everything like clustered together. In the same way, I always recommend start the same way the first two columns. You can actually change the order of those values, but the challenging thing is that when you change the order, you need to make sure that you have all four different combinations of truth and false. So when you do it in the standard way, this is the common way. If you read almost any book, they would do it exactly the same way. There's like a pattern to it, which helps us make sure that I have all of the different four combinations. True, 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 false, false, true, false, false. Just if you change the order, make sure that you have all different fours. Do not repeat combinations. Okay, so as I do this table, remember we always go from left to right. So I'm going to start with P, and notice that P doesn't have any symbols really to the left. There's no negation, so I'm just going to copy exactly the same thing. So it's going to be true, true, false, false, and that is my first step. Next, notice that I have a parenthesis. I could also have started inside the parenthesis first and come back to the P later. That is fine. The only thing is I need to simplify the parentheses before I do that disjunction, before I do that or symbol. So again, going from left to right, I went ahead inside the parentheses, and my step 2 was the negation of P. So that is the opposite values of P. If I started with true, true, false, false, then that would be false, false, true, and true. Then to finish the value of that parenthesis, I also need to do Q. Q doesn't have anything, any negation, so I do true, false, true, false. And now my step number 4 is going to be the OR, the disjunction. And remember, the disjunction is going to be true if at least one of them is true. So as I look to the left, I see false. As I look to the right, I see a true. So combining those two, I get a true. On the next one, I have false and false. So the next thing is going to be false. The next value, I see true and true. So I have two, but as long as I have at least one true, it's going to be true. And the last is also going to be true because I have a true on the left. So this is my step number 4. So now I'm going to do another OR using column number 1 and column number 4, because number 4 represents the answer inside the parentheses. So to combine 1 and 4, I'm going to start by doing true and true, which is going to be true, of course. And then I have true and false. So as long as one of them is true, then I'm going to get a true in that second row. False and true, since the right one is true, the value there is going to be true. And false and true, similarly, I'm going to get a true in that one. So this is my proof that this statement is a tautology, because I got truth values. All of them are true. So that's whenever you want to prove that something is a tautology, you want to see all truth values. Okay, so I'm going to move on to the next one. I don't have an example for a self-contradiction, but it would work exactly the same. A self-contradiction would have all of them false. So now we're going to go back and talk about conditional statements. Conditional statements are very important because they have related statements. And what do I mean by related statements? Well, whenever you have a conditional statement, there is other statements that you can create in a similar way. Now, a conditional statement is one that has if then. So you can identify it by those prepositions. If P happens, then Q needs to happen. Another way of reading that or writing that would be P implies Q. So if P happens, that implies that Q must happen as well. In symbolic form, we have an arrow. So this is our conditional statement. P is going to be called the antecedent, and Q is going to be called the consequent. So it's kind of like the cause and the effect, if you want to think about it. More other way of calling them would be like P is the hypothesis and Q is the conclusion. But we're going to leave it in this book. We just keep it as P is the antecedent and Q is the consequent. Other ways of writing conditional statements would be I could write down something that is very common is that the preposition then is not needed. So you could write down if this happened, comma, and then just state your conclusion. You could also write P happens only if Q happens. P implies Q. I mentioned that before. Not P or Q. This is kind of a strange one, but it is equivalent to also if P then Q. Every P is a Q. Q if P. Q provided then P. Notice that this one switches the order where Q is it appears at the beginning, and provided that the antecedent is at the end. Q is a necessary condition for P, and P is a sufficient condition for Q. So all of these is equivalent ways of writing a conditional statement. They all represent, all of them are represented by P arrow Q. P implies Q. So an example of rewriting the statement in a different way would be, so here I actually have the statements where I don't see the if and then. I don't have those prepositions. But instead, A says the number is an even number provided that it is divisible by 2. And as soon as I read provided, I remember this is a conditional statement. So to write it using if and then, let me give you the solution for that one. I need to identify which one is the antecedent and which one is the consequent. So when the provided part is used, the antecedent is at the end of the statement. So that part is my P, and the conclusion is going to be the number is an even number. So if I want to rewrite it, if I want to write it using if and then, I'm going to start by writing if and then P. If it is divisible by 2, comma, then, and then I state Q. The number is an even number. And these statements are equivalent. That's what the previous table showed us, that whenever these statements have exactly the same truth values. It's exactly the same statement, but it's in a different order, in a different way. Now, let's do letter B. Notice that I had 2 different examples. B says, today is Friday only if yesterday was Thursday. Again, this is another way of writing a conditional statement. First of all, let's identify which one is the antecedent and which one is the consequent. Well, when you have the only if, the antecedent is the first part, today is Friday, only if, and then the conclusion or the consequent is yesterday was Thursday. So again, I'm going to start my answer by writing if, then P, if today is Friday, comma, then yesterday was Thursday. So I accomplished the task. Huh? I needed to write this statement in an equivalent way, but using the prepositions if and then. If today is Friday, then yesterday was Thursday. And it's exactly the same meaning. Now, all of those were equivalent things. The next ones are other ways, other statements that we can create. And so the first one is called the converse, the inverse, and the contrapositive. So if you have a conditional statement, you can create 3 more, which are these 3. So these are kind of like the related statements. So if I start with a statement that has P implies Q, the converse actually interchanges the antecedent and the consequent. So we interchange the statements, or we interchange the variables. The inverse is obtained by leaving it in the same order, but you're gonna negate each one. So if you have P implies Q, the inverse is gonna be not P implies not Q. And the contrapositive, this is when you do both. The contrapositive, you interchange the statements, the consequent and the antecedent, and you also negate them. So the contrapositive looks like not Q implies not P. First of all, how do all of them look like if I apply it to a specific example? Well, in this example, I have a statement which is, if I get a job, then I will rent the apartment. And I want to formulate all the three versions. So this is my conditional statement, and I want to find all the other three. I want to know what is the converse, what is the inverse, and what is the contrapositive. Well, remember, if we just look at the symbols, the converse actually changes. This is when you interchange the variables. So to formulate the converse, then I would start by saying, if I rent the apartment, comma, then I get the job. To formulate the inverse, remember that the inverse keeps the same order, but actually negates them. So instead of saying, if I get the job, the opposite would be, if I do not get the job, comma, then I will not rent the apartment. So both of them are negated. If I get the job, the opposite is I do not get the job. And the opposite of I will rent is I will not rent the apartment. And last, the contrapositive. This is when you do both. I gotta interchange the order of the statements, and I also need to negate them. So I'm gonna start by saying, if I do not rent the apartment, comma, then I did not get the job. Now, a good question at this point would be, well, now I know how to create all three, the converse, the inverse, and the contrapositive. And if I add the original one, the original conditional statement, then I have four. Is any of these four equivalent? Like, which ones have exactly the same meaning? Clearly, they don't have the same meaning, because just by reading them, you could realize like we're talking about different things. So on the next slide, we're gonna talk about which ones are equivalent and which ones are not. So if you create the truth table, it turns out that the conditional, your original statement, is actually equivalent to the contrapositive. So that one that is the strangest, when you need to interchange the order and negate both, those two are equivalent. So your original statement is equivalent to the contrapositive. And it turns out that the converse and the inverse are equivalent between each other, among each other, but they're not equivalent to the original. So the conditional is equivalent to the contrapositive, but the converse and the inverse have a complete different meaning. In this example, we're going to determine whether the statements are equivalent or not. So the first example says, I have two statements. The first one says, if I live in El Paso, then I live in Texas, which makes sense, right? And the statement below says, if I do not live in Texas, then I do not live in El Paso. Now, when you read them and analyze them, you may conclude right away, well, yes, these make sense. So I have a feeling that these are equivalent. How can I prove that they are equivalent? Well, let's put them in symbols. Well, actually, I'm not going to put them in symbols. But if I were to put them in symbols, the antecedent, the P statement would be, I live in El Paso. And notice that on the second statement, I have the negation, and it appears on second place. I do not live in El Paso. And the same thing, I live in Texas. I changed places and I've negated. I do not live in Texas. So that's when you do both. When you interchange the order and also negate them, that's called the contrapositive. And we just saw before that if the contrapositive is equivalent to the original statement. So one could say the second statement is the contrapositive of the original. So this means that the statements are equivalent. Now, the next example, it's a little bit more mathematical. So my example B has if A equals B, and at this point, A and B could be any real numbers. So if I have two numbers that are equal, then A times C equals B times C. And C is another number. And so that's my first statement. The second statement has if A is not equal to B, then A times C is not equal to B times C. These statements, I want to know if they're equivalent or not. One might guess that they are because it seems like you're negating both of them. So it kind of like seeming would be equivalent. However, if I look at the structure that they have, notice that they don't change order. I left A and B on the first place, that is the antecedent. And the multiplication is still on the right. The only thing that I did is I negate them. So we call that the inverse, when you negate the statements, but you leave them exactly in the same place. So the second statement is the inverse of the first statement. Therefore, the statements are not equivalent. So if I have a conditional statement, it's only going to be equivalent to the contrapositive. If you create the inverse or the converse, it's considered a complete different statement. Let me move on to the next example. Okay, I'm going to go on and kind of like very quickly discuss a little bit about symbolic arguments. And first of all, what is an argument? One of the reasons why logic and all of this symbolic representation of statements is so that we can check the validity of an argument. Because we mentioned that, interestingly enough, all of this is applicable in law. People study logic in order to create valid arguments. And we're going to start by defining what is an argument. An argument consists of a set of statements called premises and another statement called the conclusion. So the premises is kind of like everything that is before, everything that you're putting as your evidence, and then your conclusion is going to be just the last statement. After all of the evidence that you presented, what did you conclude from there? So premises, everything that helps us make the conclusion. So an argument has premises and a conclusion. We're going to say that an argument is valid if the conclusion is true whenever all of the premises are assumed to be true, which makes sense, right? If all of your evidence is there, then you want the conclusion to be true as well. In any other case, like if my premises are true, but my conclusion is false, then that's going to be an invalid argument. I think I have it there. So we're going to say that it's invalid if it's not valid. So the opposite of this would be if all of your premises are true and you end up getting the conclusion being false, then the argument is invalid. And as I say true and false, you should be thinking of a truth table. So we're going to actually use truth tables in order to check the validity of an argument. Now, here we have an example of an argument. It says, if Einstein was human, then Einstein was mortal. Einstein was human, therefore Einstein was mortal. If you read it, you realize that there's a conclusion, and so this preposition, this word, is telling us that that's our final conclusion. So everything else is actually a premise. And as we break it down, if we look we could use the grammatical cues kind of like as clues to identify how many premises and how many statements we have. So notice that the whole thing, the first sentence is actually a statement. It's one premise, and it's in a conditional form because we have the if and then. So our first premise is going to be if Einstein was human, then Einstein was mortal. And we also have separate, and we can look at, we have a period, so there's a new sentence or a new statement. Second premise is Einstein was human. Well, kind of like combining premise one and premise two, we want to conclude then that Einstein was mortal. So this is an argument, and the kind of like the diagram here show us the structure of it is composed by two premises and one conclusion, which is our last statement. Let me move on to the next. In symbolic form, if I want to represent in symbols, how do I represent the premises and my statements? Well, my statements, I'm going to use letters. I change it for H and M just to remind myself H was the part that says human and M the part that says mortal. And so the first premise was a conditional, so I can write it as H arrow M. Or as I typically, when I read it, I only say H implies M. The second premise, let me go back, it said Einstein was human. Well, that's exactly H. So premise number two is represented with the letter H. And notice that this line on the bottom is to kind of like to emphasize the last part, that here comes the conclusion. So the conclusion is going to be M. Notice that in symbolic form, we use these three dots kind of in a triangle shape, and not just for logic, not just for this, but in general, whenever we do proofs, we always use those three dots to put our conclusion at the very end. And we can think of it as it is translated as therefore. So if I see the three dots, I always read it as therefore. So H implies M, and H, therefore M. So this is my whole argument in symbolic form. I have an example to write down this argument in symbolic form. So I have, she gets on a plane, or she will regret it. She does not regret it, therefore she got on a plane. And this is very similar to how you see it on the homework. So I've noticed on the homework, not always it says like, use this specific letter to represent. But I noticed that there's a parenthesis in there, which indicates the P for plane would indicate use the whole first sentence is going to be represented with the letter P. And similarly, she will regret it is going to be represented with the letter R. And I have my or preposition, so that's the disjunction. So to represent this argument, my first statement would be P or R. Then I have she does not regret it. Well, if R represents she will regret it, that is the opposite. That's the negation. So my second premise is going to be not R. And my conclusion is going to be not P. I'm sorry. My conclusion is going to be therefore, no, not P. I have the three dots, which means therefore P, because that's what I have here. Huh? Therefore, she got on the plane. And I have she got on the plane, that's just the letter P. So this was just an example of how to write. That's kind of like the first thing that we need to do, huh? Every time that we have an argument, we need to start by writing the argument in symbolic form. And this is how we will write it. Okay, our whole goal is to determine if the argument is a valid argument or not. And so one way of these are the steps to check. This is the procedure to know the validity of an argument, whether it's valid or invalid. So the first thing is we're gonna write down the argument in symbolic form. We just practiced doing that in the previous example. Number two, we're gonna construct the truth table that shows the truth value of each premise and the truth value of the conclusion for all combinations of truth values of the simple statements. So remember that our simple statements are the original letters. Like if I only have two, in the previous one I had P and R. So those are my two simple statements. And because it's only two, I'm gonna have like 4 different combinations. True, 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 false, false, true, and false, false. And the last step, and I notice I put a number 1 in there. So step number 3, it says, if the conclusion is true in every row of the truth table in which all of the premises are true, the argument is valid. If the conclusion is false in any row, that should say like in at least one row where all of the premises are true, the argument is invalid. I mean, it is accurately written, but what I mean is, and I have read it before, that was the definition of how do we know if an argument is valid or invalid. If all of my premises are true, then the conclusion has to be true. If I have at least one row in which all of the premises are true, but the conclusion is false, then the argument is going to be considered invalid. An example of this would be the following. It says, determine whether the argument is valid or invalid. And I went back to the example that I started with. It says, if Einstein was human, then Einstein was mortal. If Einstein was human, therefore Einstein was mortal. And I had already written this argument in symbolic form. So that's my step number 1, which is H implies M. Then premise number 2, H, conclusion, therefore M. So this is in symbolic form. This argument is represented like that. And then I went ahead and did the table. So my only 2 variables are H and M. So I have all of the values. Notice that I have true, 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 false, false, true, false, false. And then I put all of my premises. Notice that H implies M. This is the conditional. So the conditional, the truth value of the conditional is that it is false only when I start with true and I imply false. So the truth table for the conditional has true in all of the rows except on the second one. If you start with true and then you imply something false, that's actually false. Now for the second premise, which is H, all I did was copy the values for H. So this was true, true, false, false. And the conclusion, this was M. So same thing, copy the values, true, false, true, false. Now, once I do my table, the next part would be I need to identify all of the rows in which my premises are all true. So my first premise, my second premise, will notice that only the first row has true and true. The second row has false, true, so not both of them are true. True, false, not both of them are true. And true, false again, so not both of them are true. I needed both of them to be true. So in this table, I've crossed out of, it's been crossed out rows number 2, row number 3, and row number 3. So for the purpose of this example, those rows are not useful at all. In a sense, they don't really matter. Only my first row matters because this is the only row where I have my premises to be true. And what I need to check is that in all of the rows where my premise is true, I need to check that the conclusion is also true, which it is the case. So when I was looking for those rows, I was only looking at the premise. I didn't really look at the conclusion. Well, now that I identify which rows have true and true on the premises, and since I only have 2 premises, I'm only checking 2 of them. But if I have 3 premises or 4 premises, I need to have true in all of the premises. Well, in this case, there was only one row, and the conclusion was also true. So it happened that when both of them are true, also the conclusion is true. Well, that implies, that means that this is a valid argument. That's kind of like the whole idea of the valid argument. So I could say that this argument, the whole thing, it's a valid argument because of that. Now, I think I'm getting, oh, I do have one more example. I was gonna say, I think I'm getting to the end of my example, so I might need to draw more examples. But this is my last one for arguments. The example again is to determine whether it is valid or invalid. And the argument says, if it rains, then the game will not be played. It is not raining, therefore the game will be played. And we want to know what is the validity of the argument. As we read it, it kind of seems to make sense, but let's not be surprised. In order to check this, it's better to use logic. So let's put it in symbols. Well, I'm going to represent rain by R and game by the letter G. So my first premise said if it rains, then the game will not be played. Since G represents the game will be played, then my argument is going to be R implies not G. So that was the first premise. My second premise said, and let me go back because I don't think, oh, I have the statement right there, huh? I don't think I have the statement, but it's right here. If it rains, then the game will not be played. So that sentence, that statement is represented in the first row. R implies not G. My second premise is it is not raining. Well, that's if R represents rains, that's the negation of R. And my conclusion is the game will be played. So then I draw my line to indicate that the next statement is the conclusion. Therefore, G. So this is how it looks in symbolic form. So step number 1 to check the validity of an argument is to represent the argument in symbolic form. Okay, well now the next step is to create the table. And this is pretty similar to the other one. So to create the table, maybe I could probably go ahead and do it if needed, but let me see if I could just go over it. So notice that my 2 statements are represented with the letters R and G. And I always start using the same pattern, true, true, false, true, false, true, false. My first premise was R implies not G. Well, to create the truth values of this conditional, I actually need the negation of G. So I put it there in the middle. So if G has true, false, then the negation would be false, true, false, true. And now I do the conditional between R and not G. And remember that the only time, let me just get it. The only time, every time I go into the picture, it does that. The only time where the conditional is false is if you start with something true and you imply something false. So I'm going to go from from column 1 to column 3. I'm going from left to right. So I have, this is exactly when it's false. I have starting with true and I imply something false. Well, this is false. And then row number 2, starting with true, you imply something true. This is true. And then whenever you start with false, you could imply whatever you want to. And I always tell my students, if you have a statement where you start with something false, then you can imply whatever you want to. So this is gonna be, if you start with false, it doesn't really matter what the consequent is. The truth value is gonna be true. So false, false, that gives me true. False, true, that gives me true. Now, the second premise was simply the negation of R. So I go to R and I do the opposite values. So it's going to be false, false, true, true. And the conclusion, I have, my conclusion was G, so I just copy the values from G again. And as I look at all of the rows of this table, it only has 4 rows. Huh? As I look at the rows, I'm going to look at those ones where the premises are all true. So notice the first row has the first premise is false and the second premise is false. So this row does not count. I cannot use it to determine the validity of the argument. The second row, the first premise is true and the second premise is false. So again, since they're not both true, then we cannot use these rows. So I just cross it out. But the last two, I have true, true, and true, true. So the last 2 rows would be one of those rows that I need to analyze. These are rows where both premises, or all of the premises, since I only have 2, all of the premises are true. And what I need to see is that the conclusion is always true if the premises are true. So basically, I'm looking for all truths. So if I have truths to the left, my conclusion has to have a truth. And row number 3 actually would be good, since the conclusion is true. But notice that row number 4, both of them are true, but the conclusion is actually false. Well, this indicates that this argument is not valid. Even though when I read it, it sounded like a sound argument, like a reasonable argument, this is an invalid argument because of that. And so just as a comment, whenever you have multiple premises, in this case, I only had 2 premises, but if I had 3 premises, or 4 or 5, I would look for those rows. Notice that in a previous example, there was only 1 row. Now I had 2. The number of rows that you need to analyze is not fixed, so it always changes. In this case, I had two rows to analyze. And while the first one, since all of them were true, this was a good example for a valid case. The last part is giving me an invalid argument. So as long as I find 1 row, if all of those rows I find at least 1 where the conclusion is false, then that implies that this is an invalid argument. So the whole argument is invalid because of row 4. Okay, so I'm gonna stop here. This is all from me today. So I'm gonna pass it over to Miss Patricia.
Hello. Thank you so much, Mr. Tintos, for your wonderful presentation. So we do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. And this session will also be available on that playlist later today. So before you all leave, I want to share the TBE sessions that we will have next. At 1 p.m. today, we will have a presentation with EPCC Counseling on EPCC degree pathways and resources. And we will be back next week at 11 a.m., where Math 1332 will cover Exam 2 review, and Math 2412 will cover Law of Sines and Cosines. Our 1 p.m. session next week will be a presentation on the EPCC Theater with Ted Carver. Thank you all for coming in today. We hope you all have a lovely weekend. And if you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.